Okay, I'll carry on with where I left off earlier. We finished off by looking at some of the construction properties that often go sort of overlooked. Sticking on the same theme of constructions, I want to look at sort of assignment. Now, often whenever I'm sort of reviewing sorts of projects, I'll often find that users perhaps inadvertently, they've created a range of project sort of constructions that are intended to be assigned to the model. Or when we look in detail, we maybe find that they've only assigned it to certain rooms, and they've still got sort of spaces which have the default constructions assigned. Okay. Now, the new model visualization tool that we had some screenshots on earlier allows users to see exactly what constructions are assigned throughout their building. And I find that's a very powerful checking tool for users to ensure that what's assigned throughout all of their building is what they intend it to be. I'll demonstrate that in, again, one of these models. I'll go with this one. Okay. Now, at this moment in time, again, I think it's going to be updated in the next release. The model input visualization is only available in the an Apache sort of model of the software. But as I mentioned earlier, the actual building and the real building, they share the same construction property. So we can still check that out within Apache to ensure that correct assignment is made. To utilize that model input visualization, I simply select the zones that I'm interested in reviewing, and we'll see that activates this new icon here. When I select that, I can pick from a range of different variables that I want to check. At the moment, because all of my inputs are going to have been superseded with any NCM, the only one I'm really interested in is a CDB. So that's our construction database parameters. So this allows me then to plot the constructions. So I'll start off with this one, and I'll apply it. That then opens up the new model viewer, and it will automatically color code every surface within my model depending on what construction is assigned to it. So I've got my legend up on the top right here. I don't know if that's clear enough on the screen, but I can then sort of look in at this and say, right, well, this purple band here, this is my standard wall construction. So I know that's one of my default sort of constructions. Elsewhere, I've got this green, which is my design wall construction. That would indicate to me that I've perhaps selected only a handful of spaces and assigned my construction to those. And I've perhaps inadvertently not assigned my design construction to all of my surfaces. It's a good way for me to very quickly check and see what's assigned throughout my model. So this will list all of the different constructions in place, and I can either separate it out, so it just does opaque, does glazed only. If you are looking at looking at the glazed constructions, you may want to fill in the windows. So I can make that opaque and update that, and then they go all sort of solid, so that it's obvious what constructions are assigned to those. Okay. Now, as well as just looking at what this is only telling me the titles of the constructions that are assigned. I'll often also want to look at, well, what are the thermal parameters of these constructions that I've got assigned. So I go back to my list here. I can see, right, well, I'm interested in I'll just stick with my opaque construction U value. And that's my glazed one. Okay, opaque U value based on the ISO standard. Now this is by default going from my min to max, so currently everything's right off at the bottom of the scale. So I want to modify this a bit. Rather than just looking at my min to max, I've got full control over how I review this information. So I want to change this rather from being relative, I'll set this to manual. So I'll set this between, say, 0 to 0.4. That's probably going to be around the range that all my external facade is going to be within. Apply that. There we go. So now I can start clearly seeing which parts of my facade have the greatest heat loss, which ones are the best insulated, or worst insulated, how heat losses, how the U values vary between my walls and roofs. So it becomes immediately quite apparent as to where the most insulated or least insulated parts of my building are. So again, if I was wanting to if I find I was perhaps failing or wanted to improve the performance of my building, and I was maybe wanting to address the fabric, I could open up this sort of view and then quickly assess which constructions, which areas are the key areas to target first. Because I probably want to target the areas with the poorest U values, improve those areas rather than tackle areas which are already fairly good. Now, as I mentioned earlier, and this sort of input visualization is being rolled out throughout the rest of the software as well. So I can see that being particularly useful for some of you. I think have already mentioned that you'd used it for your real building assessment. I'm using it to view what templates have been assigned to different zones, lighting gain information, ventilation rate data. Basically, any thermal input that's assigned to your model can be viewed in this sort of coloured sort of format, and that makes it really intuitive and easy to convey that information back to other members of the design team. So I'm using this very frequently in any reports that I'm preparing within my own project work. Okay. Moving back into the sort of compliance thermal setup, I mentioned earlier that one of the most significant loads within our energy model is the lighting, and the impact. I guess the proportion of CO2 that it's responsible for makes it often one of the most dominant loads within the model. I think when I brought up the table earlier, I think some of you were surprised as to see how big the difference was between some of the default values and what's essentially being applied within the notional building. So it's really important whenever you're, addressing your compliance assessment that you do give some consideration to what sort of performance will you be targeting within your design. Okay. Now, as we've sort of talked about the NCM methodology and how that contributes really towards a sort of performance gap, there are a number of rules regarding the methodology that really dictate how lighting is represented. For example, we've got a screenshot up here just showing from the room query dialog, the lighting sort of characteristics. We can see here that we've got an illuminance sort of level defined here. This is taken from the NCM activity database, and this is the illuminance level that must be used within the compliance assessment. So in this office space, for example, if we were going to be illuminating to, say, 600 lux, we would still use this, say, 400 lux sort of benchmark. So it means that, if we would be designing to 600, the lighting level within our compliance model would likely be, two-thirds or one-third lower than it would be in reality. Likewise, if we're designed to a lower lux level than is in here, then what we use in compliance is going to be greater. So it does result again in this discrepancy between real life and the compliance sort of model. Now, users can specify there's probably two legitimate mechanisms for entering the lighting performance of your space. Firstly, you can enter it as a lighting power density. It would be best if I jump into the model just to illustrate that. So I'll take just one of my office spaces here. Compliance. And if I jump into a room query, there we go, and onto internal gains, I can see this is currently at my default levels. So it's telling it because it's this office space, it's automatically attributed this 400 lux. We've also got our default installed lighting power density of 3.75 watts per meter squared per 100 lux, giving me a total lighting power density for this space of 15 watts per meter squared. Now, what this also sort of illustrates below is it follows the same equation that the notional building uses, which I mentioned earlier. The notional building will assume a constant luminaire efficacy of 55 lumens per circuit watt. And it applies this curve, which is based on the ratio between wall and floor area, to arrive at a suitable lighting power density. So following that same curve, this would be assuming that the luminaires within this space only have an efficacy of 32 watts per lumens per circuit watt, so a good bit lower than than the notional building. Now, what I could do if I had the design lighting information available it would be to override this. So I could take it off template and say, well, it's not 3.75, perhaps it's 2.2. That will then automatically update the effective efficacy value, which is calculated here, as well as all my other internal gains attributed to it. Now, at the earlier stages of the analysis, the likelihood of having the design lighting data is pretty slim. Now, the NCM modelling guide changed, I think, in January this year. Previously, it wouldn't permit, or the rules didn't really permit you to use anything other than the design lighting power for your compliance assessment. It does now, however, allow the inference option to be used. When I use an inference option, rather than specifying a design lighting power density, or watts per metre squared per 100 lux, it lets me directly enter my luminaire efficacy. Well, it gives me a couple of options. I've got a list of predefined lamp types which have associated efficacies within the NCM modelling guide, but it's worth noting that a lot of these default efficacies are really quite poor. For example, here we've got the efficacy for a T8 fluorescent specified at 27.5. I think what the intention of the modelling guide is doing here is really for you to consider what sort of rather than using a standardised value, to identify what sort of threshold will we be targeting. Now, I believe the minimum efficacies that are required for the regs these days are 55 anyway, so that should be the minimum value you should have in order to meet the current building requirements. So if I wanted to match the notional building, rather than using one of these, I could specify my own value. So I could say, automatically put that in at 55 lumens per circuit watt. It will then calculate the associated lighting power density for that space. And at this moment in time, I'm on a sort of like-for-like basis with my notional building. Now, it may well be that I'm not just wanting to match the notional building. I may want to exceed it. I want to maybe target 60 or 65 sort of lumens per circuit watt. So again, I can use this inference option to specify what I'm sort of shooting for. And again, that will automatically update my lighting values there. I think for a lot of users, these have often been left at the default sort of values, largely because they were being asked for a lighting power density value that at the moment in time they were working on the project, they just didn't have that information available. And I think it was putting them at really quite a disadvantage. I think now, at that same stage, I would be inclined to use the efficacy sort of input value, where I could then target a level which is competing with the notional building. Okay. Now, I've done this on a single room sort of basis here. So I've just used room query. I've selected a space. Now, obviously, if you've got a large building, that's going to be a fairly time-consuming job to try and update each space. Now, we've got a relatively new function called tab edit. Let's see, let's pick out all my office spaces here. And this allows me to make specific changes very quickly to a large number of zones at the same time. So I've got all my thermal zones selected currently, and I can access tab edit through this icon here. I'm going to jump into my NCM internal gains. This is where my lighting is going to be sort of specified. Let's see. And I want to sort of update this. So rather than being based on lux, so I can use this here to change rooms on a layer by layer basis, or alternatively I can select all my rooms. I want all of these to be based on inference options, and I want them all to have, say, go for a 60 lumens per circuit watt efficacy. There we go. And that's all my zones updated in one go. So I think it makes it very, very straightforward to make these sort of global changes, and I think it's an improvement still in tools like the edit group attributes. It allows you to see exactly what's in each space. You can pick and choose exactly which zones you want to modify. So it gives you a lot more control. And that's just one example of the local level things I may want to edit. There's a slightly different interface between whether you're doing an SBEM analysis or a DSM sort of analysis. So rather than, if there was an SBEM, so I'll quickly change that over. I'll change my mode, SBEM compliance. then my lighting data would be on my building regs setup. You'll notice here I don't have an internal gains option. So again, I can access my NCM data here. Otherwise, it's very much the same. We've got the option of entering either the lighting design data, where I can specify the lighting power densities, watts per meter squared, the achieved lux level, which again then is used to determine my watts per meter squared value. Or alternatively, I can use my the efficacy value here. So we've got different inputs because the calculations have a different methodology behind them. And again, this can be accessed via the tabular edit dialog I had up a moment ago as well. So you can again change a large number of zones in a much shorter period of time and make the same changes to multiple spaces at once. Now, another area that's important to remember with regards to lighting is lighting controls. Now, I think what a lot of people perhaps don't realise is that probably the majority of space types within the notional building will automatically have dimming control assigned to them. I'd say there's more that do have dimming control than don't. So again, it means, going back to what I was saying earlier, we're really needing to understand what's in the notional building to enable us to keep up. So even if I've got the same lighting power as the notional building, unless I'm also matching the same level of control that the notional building has, I'm going to be at a disadvantage and would need to make up that deficit elsewhere. So I think again, in order to keep up with that notional building, we really need to be considering, having this dimming control technology within our designs. Again, like with the lighting power density, that can be set up on multiple spaces. So if I go through query again, and on my building regs tab, if I go to NCM data, we'll see at the bottom I've got a range of lamp controls that I can use. So in order to match with the notional building, again, as I said, I would need to be including for, dimming control based on photoelectric options. If I wanted to improve upon the notional building further, I also have the option for occupancy sensing. In the 2010 notional building, there's no occupancy sensing in the notional building. So this offers me one of the fairly few avenues to actually make an improvement against that building. So where we do have that technology in place, we can have a further reduction. Now, what is worth highlighting here is that whenever we've got these lighting controls, we've also got parasitic power attributed to them. So again, essentially an energy consumption required to operate those controls. What I find is that those are typically left at the default values. So say, for example, we had a photoelectric dimming control with an addressable system, and we also had, some occupancy sensing in there as well. When we start adding up this parasitic power, we've got here 0.57 watts per meter squared on the photoelectric options by default, and an additional 0.3 watts per meter squared on the occupancy sensing. That's quite a lot of extra power to have applied. Now, in my experience from looking at other people's models who've looked into the true values of parasitic power, I find that I think this is significantly greater than what they would find in design. And while it's a relatively small figure on its own, this is going to have parasitic power that's run 24 hours a day, 7 days a week. It does build up. And a model I looked at recently, it accounted for something like 3 kilograms of CO2 of the buildings of BER. So slashing that, made an enormous difference. It had an enormous impact. 3, yes. It had a huge impact on the performance. Now, that was perhaps exaggerated for a couple of reasons. Earlier I mentioned we looked at perimeter zoning. Now this particular model didn't have the perimeter zoning applied. So rather than just having this parasitic power assigned to the perimeter zones, it was applied to the entire floor plan. So that emphasised that a little bit further. But again, that's not that's not untypical of models that we've seen in the past. This is also going to be, or the parasitic power here is also going to be substantially greater than what's applied in the notional building. I think it uses 3% of the peak load, of the peak lighting sort of load, which is typically going to be significantly lower than those sorts of figures there. So again, we're on a back foot against the notional building. So it is worth considering, what an appropriate value would be here, because I think the default is very much on the high side, and realistically that could be a good bit lower in your design, and that can, I say, have a fairly profound impact in the resulting building emission rate. Okay. Okay. One of the other areas we regularly get sort of questions on is the auxiliary energy. I think a lot of people see it as a black box. They put in some information about their system. They get out an auxiliary energy figure sort of at the back end. Now, as I think we mentioned earlier on in the day, the auxiliary energy method that gets done in compliance is somewhat simplistic. What this table shows here is a range of the air-based systems which are available for selection in a UK compliance sort of method, and then the NCM equation that's attributed to them. So we can see that although we've got, let's see, what is there, maybe a dozen different system types, there's only really 4 equations that govern the auxiliary energy attributed to them. Now, this means that essentially any system that uses anything in equation 9 will get this, assuming the same specific fan powers and the same other inputs are the same, will get the same auxiliary energy value. As I say, I think that's something of a simplification compared to what we can do with with Apache HVAC that Sarah demonstrated earlier. But currently with the with the NCM framework as it is, this is a calculation methodology that we need to use. What we tend to find is that anything that uses equation 9 will typically result in really a very high auxiliary energy figure, and often one which is much greater than in the notional building. So typically, on a typical basis, you would find that if you opt for either fan coil units or sort of indoor packaged VAV system, you're going to end up with a much lower sort of auxiliary energy value. Now, I think that's again one of the perhaps sort of limitations, I guess limitations would be the right word of the methodology, in that you're looking to pick a system that's going to give you the best compliance result, which may not necessarily be the best result for your real building. So it's always worth considering when making design decisions sort of based on this. What are the implications for the real design as well? Is a fan coil system really going to be the most efficient and the best performing and the most appropriate system for this building type, rather than simply pick it because the compliance assessment says that's the way to go. And I think with tools like Sarah was showing earlier, with the auto sizing capabilities within Apache HVAC, it means that you can very quickly take a model and you can try out and you can run sort of detailed HVAC assessments for a range and for a variety of HVAC systems, getting sort of much more accurate figures to identify, well, how is this going to stack up in my real design as well. Now, to give so there are 4 equations there. I've tried to, graphically illustrate what those different equations are doing, or how it then takes the equation and takes that to an overall SFP. So system 8, this was essentially typical of our fan coil system. So this is the calculation for fan energy. So it's taking our NCM ventilation rate, which will be expressed in litres per person, and then it's multiplying that by our specific fan power unit for our central air handling units. That's maybe going to be in the region of 1.5, something like that. Now the airflow required for heating and cooling is then calculated on this SCR sort of value multiplied by our fan power sort of unit. So it's essentially determining, based on, it's identifying what is the peak heating or peak cooling load within our zone, and assuming an 8 degree delta T, how much airflow do we need to recirculate in the space in order to meet our loads. And then I'll multiply that by whatever terminal unit SFP you've got. So that's probably going to be in the region of 0.3 to 0.5 watts per litre per second. So with this type of system, the bulk of the fan energy is going to be, or the bulk of the airflow is being put on onto your much smaller fan, hence the much lower auxiliary energy value. System 9, this is really our centralized centralized plant. So it's doing the same sort of thing. It's just calculating, well, how much airflow do we need to supply to the room, assuming an 8 degree, so delta T. But rather than multiplying that by our terminal unit with a low SFP, it's then multiplied by our central SFP, which is going to be about 1.5. So hence the reason that this then bolsters the overall auxiliary energy value. Now I think where this starts to again lose some of the detail that we can get out from the Apache HVAC assessment is this auxiliary energy value is applied throughout all of the occupied hours. So in a system where you've maybe got fan coil units, but for maybe a quarter of the year, a third of the year, there's no heating or cooling load required, you've still got this auxiliary energy associated with this fan. Likewise, if you've got a VAV system, again, our auxiliary energy value is still based on that fan operating at its full capacity. So I think there are a lot of issues which result in, I guess, a compliance calculated auxiliary energy value typically being a good bit higher than what you might expect based on that system had it been modelled in something like HVAC. So I think it's again when you're considering what your key loads are going to be in reality, it's always worth sort of bearing that in mind. Okay. Now I think what came out from the sort of tests I've been doing recently and looking at sort of customer models was that a lot of customers weren't aware that there were a number of local level sort of system settings that can be set, which will have a big impact on the overall performance of their system. Now, if I've got a fan coil system or anything that uses that equation 8, then whenever I go into my system query, I'll have this terminal unit SFP. However, this is only available if I've got that system type in place. Again, the default sort of value for that is set at 0.8 watts per litre per second, which is again a good bit higher than the notional building, which will be using sort of 0.5. So unless the user knows that's there, they go in and they make sure that their terminal unit SFP is appropriate for their system. They're again on the back foot against the notional building. Now, while I'm on this dialogue, much like with the occupancy sensing, we've also got the option to set demand-controlled ventilation, regardless of whether it's a mechanically ventilated space or a naturally ventilated zone. The notional building doesn't have any demand-controlled ventilation, so this is again another avenue where we can start to claw back some credit against the notional building. This can save us on a couple of areas. If we've got demand control vent, we're reducing the amount of fresh air which is being supplied into the space, meaning that our heating loads are dropping as a consequence of that. But also if our heating loads are dropping, our system doesn't have to work as hard, so we'll also find that our auxiliary energy drops as well. So we can see a double benefit by having if we're able to sort of incorporate the demand controlled vent into our design. Okay. Now, I guess on the same sort of topic as we sort of talked about earlier with sort of default values that are in place that often get left at defaults, I often find that the losses attributed to any domestic hot water systems are often often much higher than they would be in reality. Now we've got some figures in place here for the circulation losses on secondary loop. By default, again, we've got that set at 21 watts per metre length, which is a very pessimistic sort of value. And also, I'm pretty sure the storage losses, the default value we've got in there, which is expressed in kilowatt hours per litre per day, is again a fairly pessimistic value. So I often find that people if these defaults are left at that, then they're again they're a back foot against the notional building, and they're using figures that in reality they'll probably be performing much better than. To give what I quite often use for as a guide for what sort of watts per metre length would be sort of expected for this domestic hot water system. I've got here an extract from the Non-Domestic Building Services Compliance Guide. This gives the recommended maximum losses for various types of pipes. So for our hot water system, we can see that a value of 21 would be indicative of a pipe with a diameter of about 139, probably about 150 mil sort of outside diameter. So unless we've got an extremely large DHW pipe running through our building, it should be an awful lot lower than what we're using here. Again, these are all small small components, but collectively they can add up to a fairly substantial have a fairly substantial impact on the resulting BER. One other thing that I see quite often, if I jump back again, getting ahead of myself, is quite often I'll often see users with multiple systems, much like I've got here. In fact, I've set this up to deliberately sort of illustrate that. So I've got one Apache system set up to handle my domestic hot water loads, a second one set up for my meeting room fan coil units, and a third one set up for my offices. Now, in each of these systems, I've got a storage tank with losses, and I've got secondary circulation with losses. So rather than just having that loop accounted for once, I've got it accounted for maybe 3 or 4 times within the same model. Again, it's a small load, but it all adds up. The last step I was wanting to look at is, once we've set up our model, we've run our analysis, we really want to understand what are the results telling us. If we still need to make some savings, what's the best way for us to improve this particular model? Now, within the navigators, the second automated report that gets generated is a dominant issues survey report. So I've got a couple of screenshots from this here, and I can open up one of my models. So the first part of that dialogue is it identifies all our different end uses, and it compares the actual and notional side by side. This means that at a glance, I can instantly see, well, which of my end uses are the most dominant, which are responsible for the greatest proportion of CO2 emissions, and which regions am I performing much worse than in the notional building. So I can see from glancing at this that, well, lighting is the most dominant CO2 emitter from my building, and my notional building is, actually, and this is one that's set up to be fairly good. So I'm doing quite a bit better than in the actual building and in the notional building. But we can start using this to highlight where the greatest savings can be. After that, the report will automatically sort of structure some recommendations just to say, well, here are some areas where you can make some savings. So it's comparing again the actual and notional. In this case here, auxiliary energy was deemed to be one of the most dominant sort of loads. And then it allows me to break it down into the different systems for the actual and notional building. So I can start seeing, are there any areas, any particular systems where the notional building is performing better than the actual building. And it then gives a couple of suggestions below that as to how that can be improved. I'll open up one of those reports from a model here. It's what the report will do is, as well as just look at the different end uses, it will start breaking down, well, what's constituting that end use. For example, if on the heating energy, as well as specifying tell me what my overall heating load is, we'll then start breaking down, well, how much of that is attributed to ventilation, how much is attributed to infiltration, how much is attributed to conduction losses. So if I then wanted to improve upon or reduce my heating load, it gives me clues to how I'm best going to do that. Is it through improved heat recovery? Is it through better management of ventilation? Is it through improved air tightness, or through improved fabric measures? So this particular report I can only access once I've run a simulation, as it needs to have the simulation results that I can pull out and it can draw information from. Whereas the inputs one, I don't need to have that. Okay, so it tells me straight away that most of my inputs here are still set at default values. So I'm a long way off hitting compliance. It tells me straight away that I'm failing, and by quite a large margin. What I can then see is identify, well, where is the the majority of my CO2 attributed. So my take on this is that I think the first two areas I'd want to address, again, would be my lighting. I'd want to bring that down to make sure it's at least competing with the notional building. And again, on the heating. So again, my default fabric properties are, again, a lot poorer than that of the notional building. So these are the two areas which I would probably want to, if I was looking to make improvements, that's where I would focus on sort of first of all. And then I think I'd probably move on to auxiliary energy. So this again allows me to visualize my two different sort of building models. Okay, so it's determined that my lighting is going to be the area I'd want to target first off. It then gives me a summary report showing all my actual and notional lighting power densities, watts per square meter for all these different spaces. So I can see straight away where all the that's much poorer in my actual building. Also, if it was only in certain spaces that were poorer, it allows me to isolate them. And again, a month-by-month breakdown of my lighting performance. Next, as I had expected, heating is my sort of next dominant load. So again, it breaks it down into the actual and notional, and then compares fabric losses, let's see, infiltration, and let's see, I guess I have got heat recovery in there. Let me check it out. And again, sort of ventilation. So this then tells me that the majority of my heat loss is through the building fabric. So if I want to reduce my my heating load, I really want to look at improving my building fabric. And this expands on into auxiliary energy. It goes through them in the areas of least return. I think where the benefit from this sort of output, where it comes from, is it means users aren't sort of stabbing in the dark when they're trying to reduce their building emission rate. If they run an analysis and they find they're failing or they're not quite reaching the target they want, they can make an informed decision as to where I guess they'll get the most benefit for their efforts out of the model. For example, if I go back to my overall breakdown, I can see that the DHW makes up really a fairly inconsequential proportion of the emissions rate for this building. So if I was looking to reduce or to improve upon the BER, probably in this particular building, putting in solar hot water collectors wouldn't actually improve things a great deal. Even if I eliminated my my actual building's domestic hot water, I'm still going to be miles off sort of hitting the BER. So it shows me there are which areas are going to be most important to target first of all.